welcome to Chem 6161. Today we will talk about the Diels Alder. Okay, basically Diels Alder is a 4+2 cycle addition between a DN and a DNO-file. Okay, basically what is happening is that what we have is this arrangement of double bonds to generate a 6-member ring. Formally, the Diels Alder is one of the most common methods to synthesize 6-member ring. When we are talking about Diels Alder, basically we are talking about regioselectivity, that means why I choose this regioselectivity. Why I choose that the methoxide is down and the aldehyde is right. It's up, sorry, it's in the top. Well, this is based in the ortho-para rule. Okay? What means this? When I have one substituent in each part, okay, in the N and another in the dienophile, sorry, they tend, the most normal regioselectivity is when the two substituents are located in ortho or para one of the other. In this case, they are para, okay, we are following the nomenclature of the benzene rings. This is para, that means 1,4. If, for example, we have this compound, what we will have? This one. Okay? We will have the ortho. The other possibility is that we can put it on the opposite, and we can have this. Okay? If we rotate this, we will have this. In this case, the configuration will be meta. 1, 2, 3, meta. Okay? This is not favored. Always ortho-para will be favored. Another way to know which is the regioselectivity of these compounds in the Diels Alder is when we have a very differentiated electronically diene and dienophile. This diene is electron rich. We have a methoxide. This dienophile is electron poor because we have a carbonyl group. That means if we do it, if we analyze the density charge in each carbon, that means this will be negative, this will be positive, this will be negative, this will be positive. And in this case, in the aldehyde, this will be negative, this will be positive. Okay? Do the resonant forms and you will see that this is the density charge for each carbon. And then obviously negative is going to positive, negative is going to positive, and this is the regioselectivity. You can do it by the ortho-para rule, or you can do it by electronically. But this only works when we have a very differentiated electronically diene and dienophile. Okay? Then the second thing that we have to care about the Diels Alder is how is the approach of the dienophile in this case over the DE. That means we can imagine that this is the transition state. Okay, we have the diene perpendicular to the plane. Okay, this is perpendicular to the slide. Okay, and then the dienophile is coming from the bottom or from the top. In this case, it's different. Okay, but we can have two approaches. One is, I will try to draw it a little bit better. Okay, from the bottom, one is that we have this approaching with the aldehyde inside the diene, or we can have with the aldehyde opposite to the diene, sorry. Okay, we have these two approaches. Okay, both by bottom, but basically with the aldehyde far away of the diene, or the aldehyde just in the direction of the diene. This is considered the end approach, and this is the X approach. Okay? In the blackboard, I put a note about endo and X approach that I hope that you already know from the later course, for the older courses of organic chemistry, but in the case that this nomenclature is new, check the notes and you will see what is endo and what is X. In the case of the Diels Alder, the end approach is favored. That means that we will have always this approach. Okay? This is the diastereoselectivity, diastereoselective aspect. We will do it with one example. For example, we are using this compound, okay, with a metal here, and we are reacting with this acrylate. Okay? What will happen? We draw the transition state. Okay, this will be the transition state. Okay? We draw the ester going inside the diene because we have the end approach. And this will be the problem. This is perpendicular to a plane, this is perpendicular to a plane, with the ester just going inside. Okay, then what we do is to draw the 6-member ring. We draw a double bond, we draw a methoxide, and then we see the substituents. If we are forming this bond from behind, okay, what we have is that the methyl has to go inside, because the hydrogen is here. If we are forming this bond from the top, what we have is that the ester has to come inside. Okay? And that's all. This is the diastereoselectivity in the case of the Diels Alder. It's easy. We have to decide which is the approach of the dienophile, if it's endo or X in this case, and simply we check the formation of the new bonds. Okay? Okay, this is regioselectivity, diastereoselectivity.